So let's do the second part of the video. In this part, I will simulate the theory that I explained before. So let's put a current generator, and the current generator, as I said before, will be the power dissipated. I will remind you the formula. The power loss is equal to output power times 1 minus 1 over n, which n is the efficiency of your converter. So let's put the power dissipated by the MOSFET, which are equal to, in a case that I said before, in a resistive load, you can find in another video, but I will show you how to put the resistances. So this is the junction to case resistor. This is a thermal resistor, so by the way, you will have Celsius over watts for each resistor. And this is the junction to board resistance. Now, for the ground of the circuit, you have to put the ambient temperature, because the real ground here is the voltage. So let's put 25 volts as the ambient temperature. And now you have to consider that if you have also the heatsink, you will have to add 2 more resistances. The first is the TIM, which is the paste between the case of the heatsinker and the board itself. For now, let's neglect the case of the heatsinker, and just put the junction to case and case to ambient, so RCA. You can find this data, for instance, on the datasheet. I will just take the APC, efficient power converter 2022, and in this you can find the value of the thermal resistance, junction to case, junction to board, junction to ambient, 0.4, 1.4, 42, typical value. As you can see, the unit measure is Celsius over watts, because if you have a current flowing, which are basically in this thermal model, there are watts, you will have Celsius as a drop voltage. So let's do this. Let's put 0.4 as junction to case, and 1.1 as junction to board, and 42 as junction to ambient. So let's run the simulation and let's see what happens. Yes, I forgot the value of the dissipated power. Let's put 1 just for practice. So I will have just a small rise in temperature. If we put more power dissipation, and if we raise the temperature ambient to 53 degrees, which is a critical temperature for most devices, and 10 watts as dissipated power, you may have a major rise in current. By the way, this is a very efficient this is a very efficient transistor, because the power dissipation is not so high. So I want to show you what happens if you have a synchronous configuration in which you have the 2 switches very near. This kind of happens, for instance, if you use a half-bridge configuration. Maybe in most power device use this kind of configuration, in a buck configuration, boost configuration, and also half-bridge, full-bridge configuration. So what is going on? Basically, I will take you a project that I made for my thesis. As you can see, these are the 2 GAN devices which I used, and they are very near together. So I will show you the 3D model. Whenever these 2 are switching, the heat from the heat and also the track will also influence the other MOSFET. So how can you model this factor? Well, basically, you can use this model instead, as explained in the theory, because you have to take into account the spreading resistance between one transistor to another. So this is a way complex model, but it actually does the job. As I said also in the video, you can even think to add the thermal capacitances between one node to another. The problem is that these values here are not so easy to be found. As you can see in this datasheet, there is no actual value on these capacitances. So you can't rely on random values. Otherwise your simulation will become unreliable. So I want also to show you the result of this thermal model. As you can see, this is the experimental result with a thermal camera. Whenever my switching converter is switching, you can see that most of the heat is exactly on the case of your devices, like here, but there is also some heat in the tracks. So you want these tracks to be as large as possible in order to dissipate as much heat as possible, and also to put vias in order to reduce the thermal resistance between the board. So this is what it looks like a non-inverting buck boost converter whenever it's switching. The greater heat comes exactly as the case in the case of the two guns, but as you can see, you will also have some heat in between.